In this lecture, I'll talk about neural nets used for classification, mentioning how they work, some choices about how they are structured, and issues for them around understandability, bias, and adversaries. As a reminder, here are the basics of how a neural net works. There are input neurons that take in the data about the thing to be classified. There are neurons in some number of hidden layers whose weights and biases are set by the training data and generally don't have meaning to humans. And then there's output neurons corresponding to various classifications that you might have, again, with their own weights and biases set by the training data. In a very simple case, the input neurons might represent the words in a resume, and there might be just a single output neuron that says interview that could either be close to 1 if you should or close to 0 if you shouldn't. In an extremely complex case, the input neurons might represent the hundreds or even thousands of different aspects of the meaning of a context in a large language model. And the output neurons might represent the hundreds or thousands of aspects of the meaning that it thinks are relevant for the word that will come next. So rather than talking about either extreme, I'll talk about one useful example that was one of the first successful applications of neural nets. And this is to do recognition of handwritten digits. And so the idea is that the input neurons here, instead of drawing them as these little circles for the neurons, I've drawn them as the pixels in a grid. In the original version, it was a 32 by 32 pixel grid with 1,024 input neurons. Here I've drawn it as a smaller grid. But then there's some hidden layers in between. In the actual original application, there were about 6 hidden layers with a few hundred neurons each. Here I've just drawn it with 3 hidden layers with 8, 6, and 4 neurons each. And then there are 10 output neurons in the output layer corresponding to the 10 digits. Each neuron has a sigmoid activation function. Don't worry about the details of what that means, except that every neuron will always have an output that is a number between 0 and 1. And the way that we train this neural net to recognize digits, what it's going to try to do is we will put in a pattern of black pixels on that grid. All of those numbers will be fed through the weights and biases until there's some pattern of activation on the neurons at the end corresponding to the digits between 0 and 9. We start with the weights and biases for all these connections at random. And I won't give you the full details of how we train it, but I will give you the outline so that you can understand the basics and you can learn much more of the details if you know a bit of calculus. But here's the basic idea. So we have some training data that consists of tens of thousands of handwritten digits. And what we're going to do is we'll put in just one of the training images and run it through the neural net. Because the weights and biases in the neural net are just random, this first run is just going to output some random numbers for these 10 different digits. But they're all numbers between 0 and 1, as you can see. Now, because this is in the training data, we know what digit this input is supposed to represent. It's supposed to be a 2. And so most of these outputs need to go down. They need to be as close to 0 as we can. But the one for 2 needs to go up. It needs to be as close to 1 as possible. And so what we do in the training is we see how far is each one from the correct value that we know. And we use this to calculate how much do those outputs need to go down or up. And then what we do is we see which weights in the connection from the second to last layer to the last layer, which of those weights could we tweak that would make the results be closer to what is needed. So then this is what this is illustrating here. But then once we figured out what tweaks to the weights on the second to last layer would be helpful, we also look at, well, given the weights as they currently are with only a little bit of change, which of those would be helpful to raise and which of those would be helpful to lower? Here I've just found some ones that are highly connected to some things that need to go down and said they need to go down, some things that are weakly connected to the thing that needs to go up and say it needs to go up a little bit. But you'd use some calculus to figure out what you need to do. And then we figure out that sort of change in the second to last layer means we need to change all the weights on the third to last layer by some amount. And then we repeat the process going through all of the different layers and just figure out which tweak to all the weights and biases would make the output get a little bit closer to the correct thing. And that's what we do with a single piece of training data. Then, since we've got tens of thousands of these handwritten digits, we just put in the next one. In this case, it's supposed to be a 3, so we do the same calculations, and we're working backwards from the end all the way to the beginning. That's why this is called back propagation. And we figure out how to make it just a little bit closer to the correct answer for this one. And then we go through it for all of the tens of thousands of pieces of training data. And once we've gone through each piece of training data once, then it's going to be better, but it's still not going to be great. So we'll just go through all the training data again, tweaking all the weights and biases just a little bit each time to get it closer and closer to the correct answer. And after we've done this a few thousand times, going through all the training data, we'll eventually hopefully reach a network that does a good job of classifying all the digits that were in the training data. Now, this is what we do. We start with the training data and set the weights and biases on the network. But if we're smart, we hold on a bit of the training data and use this as a test. We want to make sure that it didn't just memorize the specific things in the original training data, but actually got a good set of weights and biases that can generalize to other examples. And so we hold out a bit of the training data and call this validation data or test data. We use it to test how well the neural net is doing and validate that it actually learned the pattern rather than just memorizing individual pieces of data. If it does well in this validation, then we say that it's done and we start trying to put it into practice. And maybe we look for further issues that come up once it's in practice. But if it does badly on the validation, then we change some things and try again. We may try to figure out, maybe it'll work better if we have more hidden layers, or maybe with fewer hidden layers. Maybe it'll work better if there's more neurons in between, maybe fewer neurons in between. Maybe this is actually the right architecture, and we just need to restart from a different random seed. But that's the idea, that the validation data can be used to figure out whether you have actually done a good job of learning the pattern rather than memorizing what's on the test. Now, at this point, it's very hard to interpret what any of the neurons in the internal layers are doing, but there are a few things that we can do to help. And as a very simple thing, first, let's look at what we could do with some handmade weights on some of these neurons. So let's imagine that we've zoomed in on just a 3x3 set of pixels in the input, and then we're looking at a single first hidden layer neuron that those are connected to. And let's say we specifically put in these sets of weights, where we've got the neurons on the right end of this 3x3 segment all count positively, the neurons on the left side of this 3x3 cell all count negatively, and the ones in the middle count at 0 weight. So now, if the input happens to have 3 vertical black pixels here and 3 vertical white pixels on the left, then this will result in a weight of +3 into this first layer hidden neuron. If we have the opposite pattern, then we'll get a -3. And this is what happens whenever there's a vertical line that goes somewhere in this little 3x3 grid. It'll respond very strongly, either strongly positively or strongly negatively. Whereas if we have a horizontal line here, one of the pixels gets counted positive, one of them gets counted negative, and it all cancels out. So the neuron reacts at 0. If we've got a slightly more complex pattern where it's not fully on or off, but on those neurons, but it's still largely vertical, it'll still be a largely positive pattern. And so what we might say is that this set of weights in a 3x3 grid of neurons will make the next neuron that they're feeding into a vertical edge detector. And will represent that set of weights by this sort of graphical pattern that it responds to most strongly. And now, sometimes when we train our handwriting recognition neural net, it might somewhere in there have a neuron at the first hidden layer that works like this. And we could figure this out if we look at the weights and see if there's any that happen to have this sort of pattern. Now, if there's a few hundred neurons in that first layer, very often we'll have some vertical edge detectors in there that are looking at certain subsets of the initial input. Maybe there's going to be some horizontal edge detectors near the top for helping us identify the number 5, and some vertical edge detectors in the middle for identifying the digit 1, and maybe some vertical edge detectors on the right for identifying the digit 7. But what you really want for a smart and understandable image identifier is some sort of edge detector that could be applied at every single point in the visual field, rather than having one neuron specialized as an edge detector for one point and just hoping that the network happened to come up with a similar thing at another point in the array. And so what they found is that rather than having hundreds of unrelated neurons on that first hidden layer, they would make a whole grid of neurons in that first hidden layer that correspond to all the positions uh, in the array of pixels. But instead of each one of those having its own weights, what they do is they have one set of weights that gets applied to the entire input for one set of copy of neurons in that first hidden layer, and then another set of weights that gets applied to the whole grid for each of another set of neurons in that first hidden layer. And then what we can hope is that maybe there will be one of these sets of weights will be trained to be a horizontal edge detector that can be applied everywhere and then used in later calculations. And another one might be a vertical edge detector that can be applied everywhere and used in later calculations. And maybe the training data will help it find some other patterns that are useful to try to identify at the beginning. And these little patterns, like the horizontal edge detector pattern or the vertical edge detector pattern, they call these kernels. And you can think of them like the little kernels on a corn cob that somehow together make up the whole grid of the cob. And introducing these little kernels that get repeated at every single segment of the initial set of pixels meant that more data passes through the neural net. There's more neurons at these higher levels. But instead of making it more complicated, it actually makes it simpler to train because you only have to train 9 weights for this kernel to then get a whole grid of information at the next level, as opposed to training 1,000 weights for one pixel and 1,000 weights for another neuron and 1,000 weights for another neuron. You just get 9 for an entire grid and then another 9 for an entire other grid. You get more information at the next level, but easier training. And furthermore, these weights and biases that form these kernels are often going to be much more interpretable for humans. So you get a lot of advantages by doing this. Uh, and Here is an image from a 2012 era neural net called AlexNet that it was trying to identify thousands of different types of images from color inputs rather than just identifying the 10 different digits from black and white inputs. And here are some of the kernels that it identified. And we can see something about what this neural net is looking for by looking at that. This sort of structure where we've got all these kernels that are each trained to look for a different thing in the pixel array that then gets sent up to the first layer is called a convolutional neural net. The word convolution has a whole history in mathematics that you can look up if you're interested in, but doesn't really matter. And so this is one advance that they made in training image recognition. There have been other similar changes to the structure of how are all the neurons connected to each other that have been done for other sorts of processes. So if you're interested in processing data that comes in over time, like maybe voice recognition or speech recognition, there's this thing that they call a recurrent neural net. If you're trying to take in neurons that represent meaning, it turns out that the transformer and attention pattern that we see in large language models was really useful for that. Uh, but in 1989, a convolutional neural network designed by a team led by Jan LeCun who's now at Meta. At that time, he was at Bell Labs. It was good enough at identifying handwritten digits that it started being used by the US Post Office. However, although that was good enough in 1989 for processing digits for handwriting recognition, it wasn't until 2012, this AlexNet that Jeff Hinton and some of his students at the University of Toronto developed, that they were able to do better than symbolic AIs at many other kinds of things. And for that, they needed a lot of the more advanced computer processors that were available in 2012. Now, uh, there are more techniques that have been developed since then for producing somewhat more understandable neurons in a neural net. One of the big breakthroughs came in 2015 when a team at Google was trying to reverse engineer some of the neural nets like AlexNet. So they realized first you could take an image, feed it into AlexNet. This is what the AlexNet pattern looks like. Uh, and then it would output a label here. And this has 1,000 different labels because it's trying to identify 1,000 different types of object. But then they realized, well, you could start with the label and then try to figure out what pattern of pixels would excite that label neuron very well. And it turned out when they did that, they got something that looked like this. And they realized this is sort of what the neural network imagines a banana most ideally looks like. And they called this system Deep Dream because they thought of it as like, what would a neural net dream of if it was just imagining things for these labels? And then uh, another thing they realized they could do is feed in an image, see how it labels it, and then pick some random neuron in the middle of the neural net and see what changes to the image would make that neuron get more active. And here we could see that in addition to just creating a generic image of an ibex or a generic image of bananas, it could take an ibex and then try to understand what is this neuron doing in the interpretation of the ibex. And it seems to be doing, who knows what that's doing, but we get some better understanding of these internal neurons. And they started to realize just as the first layer might correspond to edge detection, maybe higher level layers are corresponding to other aspects of style or a meaning in an image. And this idea was eventually developed a few years later into what they call the diffusion models that take prompts and generate whole images like DALL-E, Stable Diffusion, and Midjourney. And in mid 2024, Anthropic did a similar thing with their large language model, Claude. They figured out how to identify meanings for individual neurons in the neural net. This is a thing they call Golden Gate Claude, and it's worth looking into to see how it might help us with understanding the meanings of things in neural nets. None of this has given real interpretability. It's not like a symbolic system that can just tell us, I applied this rule to get this result, and you could then think about whether that rule makes sense. Here, we're getting some understanding of what's going on in these neurons. Now, one of the other interesting things that came up during Deep Dream, they looked at what happens if you put in the word dumbbell and see what is its ideal activation for a dumbbell. And what they found is based on the images that it was trained on, it's not just getting the dumbbell. Almost all of the training images that were labeled as dumbbell had someone's arm holding the dumbbell. And you might even be able to see something about the racial identity of the people who were in those pictures. And this leads to the next topic about what goes on with neural nets, that a lot of the quality of the judgments that the neural net is making will depend on the quality of the training data that you gave it. And sometimes neural nets learn to identify something that you didn't intend, but was there in the training data. So here's one example. This was a neural net that was being trained to identify different species of fish. It was meant to be able to automatically detect if someone is catching an endangered species and tell them to throw it back. And so in order to do that, it had to be able to work from cameras that are just on the fishing boats in this very noisy environment. And so they used those sorts of images as the training data, which is a good idea. Now, we look here at some of this training data. I had trouble finding the fish in these images. I think this is all the fish, but maybe there's some others. Uh, Now, the fishers who sent in the pictures had labeled each of these pictures with what species of fish are in it, and the neural net was then trained to match that. And the neural net did do a good job with the training data, and it even did a good job with the validation data that they had held back. But when they tested it on new pictures taken from new fishing boats, it did very badly. And it turns out what was going on is the different fishing boats that submitted the training data were fishing in different oceans. And so they were catching different species of fish. And instead of just looking at the fish and trying to just identify the fish, the neural net had learned, what does this boat look like and which species are on this boat, so that it had a much simpler image identification problem on the fish. It was using the information of the boat to guess what fish it was. And so when new boats started submitting images, it had no idea which species might be the relevant ones. And this same sort of thing happens in many other applications. There was a neural net that was being trained to identify internal conditions from X-rays, and it had training data from a bunch of different hospitals. But it turns out one of the hospitals was treating lung injuries, another one was treating broken bones, another one specialized in cancer. And instead of looking at the X-ray to figure out which issue was going on, it was identifying the signature of the hospital technicians from the different hospitals and said, oh, if this signature is on there, it must be a broken bone. And if that signature is on there, it must be cancer. And so it wasn't doing what they wanted at all. It was learning how to identify patterns in the test data. But the issue is, what's the data that you're giving it? Now, this leads to general other issues that if you if you try to train the neural net in one context and then test it in another context, it's not always going to work. So for instance, maybe you have a neural net that's been trained on images of courtrooms in the Great Britain, and you're trying to train it to identify who's a judge, who's a lawyer, who's the client, and so on. Uh, if you're training it on data from the UK, it's going to be paying a lot of attention to those wigs that the people are wearing because judges wear one type of wig, lawyers wear another type of wig. Usually the clients don't wear wigs. And if you then try to apply this neural net in the United States where no one's wearing wigs, it's going to have a lot of trouble. And now that's a sort of playful example, but a more serious example happens when you try to train a neural net to identify faces or to identify facial expressions or anything like that. If most of the faces in the training data are people of one sort of racial identity, then it's often going to have difficulty identifying, extending its training to apply well to people of a different racial identity. And so one of the things that neural net researchers these days are very interested in is how do you make sure that your training data includes adequate representation even of groups that might be small groups, but could be very important for the applications that you're interested in. And this sort of thing happens in more obvious ways as well. If your training data has lots of women who are nurses and men who are doctors, then if you try to identify who's the man, who's the doctor, and who's the nurse, it might get things wrong if it sees people in unfamiliar roles. And of course, this is exactly what humans do too. If humans have a lot of experience with male doctors and female nurses, and they're not used to understanding what uniforms people wear, they might misinterpret who is in which role in these images as well. This is how subconscious bias works. Even if you explicitly know that women and minorities are often in positions of authority, if someone doesn't look like your internal feeling is of how you feel an authority figure should look like, you might not listen to them as much. And so it's notable that neural nets replicate the same kinds of bias that humans do. Now, one final issue that is of intellectual and academic interest, but may or may not be of practical interest, is what they call adversarial images. So if an adversary, someone who wants to fool your neural net, has access to your neural net to see how it classifies various input images, they can actually create images that the neural net will classify very confidently in a way that no human would. And interestingly, the way that they create these images is very parallel to the process of training the neural net in the first place. But if you look at these two images, you probably can't even tell the difference between those two pandas. But that little noise in the middle is the difference. And someone figured out if you add this noise to that image, then a particular neural net will misclassify it. And so the way this works is that uh, if, so we first take an image, pass it through the neural net, and see how strongly are the various output neurons activated by this image. And you often want to start by looking for an image that it's fairly confident, but not 100% confident on. So maybe it starts with an image that is 83% confident it's a banana, 15% confident it's a telephone, 2% chance it's something else. If you're the person who's training the network, what you do is you look at this and you say, well, I want to tweak a few of the neurons inside, maybe raise a few, lower a few, in a way that makes it slightly more confident that this is a banana, because that's what it should be saying. But the people who are making the adversarial image, they keep the neural network fixed, and they say, let's take this original image with this original classification, and let's just tweak a couple pixels of the image and see which tweaks of the pixels make it do the wrong thing at the end. And so you need to have access to the neural network in order to generate these kinds of adversarial images. Uh, now, if you're just looking at a single image, if you're just trying to create a single image, you can often create a single image that the neural net will very confidently miscategorize. Whereas the training data training the neural net takes a very large amount of computational power because you're trying to make it do a good job on millions and millions of images. Whereas creating the adversarial image is much easier to do because you're just trying to make it do a bad job on one image. These couple hundred pixels that you figured out how to modify are unlikely to apply very well to other images. Now, furthermore, since you're operating directly on pixels, this will often apply to something that classifies still photographs. But if you're trying to make an adversarial way of labeling a stop sign, some change to the physical world that will cause a camera hooked up to a neural net to misidentify it from many different angles, that's much harder. There are some papers that are out there that have shown that maybe you can do this with certain of the self-driving car systems. We're not yet sure how robust this really is. Another thing some people have noticed is some of these adversarial images, this was an image that is a photograph of a cat on the left, and they tweaked it in a very subtle way on the right to make a computer think it looks like a dog. Now, what they noticed is a lot of people looking at this image also think it looks like a dog. And so there's lots of adversarial images out there that work on humans too, though the way you make it fool a human is often going to be very different from the way that you make it fool a computer. There's, of course, many other problems that you can create if you can directly hack into the camera or if you can tamper with the training data that the neural net is trained on. Hopefully, those things are less significant in practice. And of course, this sort of thing can often be done with classifiers for things like resumes other than images. Maybe just tweaking some of the fonts and spacing will make the resume neural network decide this is a resume that must be interviewed that in a way that might be unnoticeable to a human. That's an interesting question for further research. Okay, so just to summarize, neural networks can be trained by backpropagation. You give it a bunch of training images, tweak the weights and biases, and hope that eventually it classifies them all well. For images or other specialized uses, different architectures than a complete connection at every level can be useful, the convolutional network. It's hard to interpret a lot of the internal neurons, but there is some progress. Both the convolutional and the recurrent structures give you some insight, and then the deep dream and further things like that have given us some more insight, though it's still hard to interpret. If your training data doesn't fully match the application entirely, the network may often have turned out to learn the wrong thing, just as humans often learn some stereotypes and prejudices rather than the real pattern that actually matters. And then there's interesting cases where it's possible to craft specialized inputs that will fool the neural networks.